Hello, everyone, and welcome to our online series of statistical lectures for undergraduate psychology students. Today, we will talk about our last big topic for the first module of topics, the central limit theorem and normal distributions. Standard z-scores, which is our first subtopic under this title, can be found in chapter 6 in the minimum book. And I will start with a real life research problem that I myself had when conducting reaction time studies. Response time measures were collected from male and female students in two experiments, word reading and picture naming. And in these two experiments, as you can see, the setup is very similar. We have a computer screen, and in the speeded experiment, many research subjects respond in word reading with the word dog, and in picture naming, the same with the word dog. But here they read the stimuli, here they see a picture of a dog, and hopefully they recognize the dog. Now, what I wanted to test if there were any sex differences in cognitive performance, straight as that, but I wanted to use both experimental data. What could I do? Well, the problem is that the two experiments are different, as we've highlighted. Moreover, not the same number of people and not the same number of males and females were in the two experiments. And response times, not surprisingly, are generally slower in picture naming experiment, much slower in picture naming experiment as in word reading. So given the male-female ratio is different in the two experiments, it's just impossible to compare the raw reaction times and draw a conclusion for male and female differences in cognitive performance. Why is that? Just a note. Well, because if there were more females in the, let's say, picture naming experiment, then our results for the picture naming were overrepresented by the females, and since we know that this task is much slower, it would give us a false result. So the mean samples in this reaction times are different. Just to summarize, we cannot compare the raw reaction times. We could go back and test exactly the same number of girls and boys in both experiments, but hey, who wants to do that, right? It has been hours of data collection procedures, but there is a solution. We can simply standardize the raw data and thus work with the standardized data in the comparison of male and female performance. So that was the problem. This is the solution. But what does it mean, standardization or z-scores? That's the common name in psychology that we use in statistics related to psychological experiments. So the standard score or z-score expresses a score's position with relation to the mean of the distribution, using the standard deviation as the unit of the measurement. You can see the formula here. You take each value, you subtract the mean value of the sample and divide it by the standard deviation. If the z-score value is positive, the original score surely lies above the mean of the distribution, whereas if it's negative, then the original score is definitely below the average performance. Now, this is what happens when in SPSS I ask the program to make z-scores from my raw reaction time data. This is the distribution, descriptive statistics of the word reading reaction time in its raw format. And this how it looks like when I make z-scores of it. Well, basically the shape of my distribution is very, very similar, but please notice here that the average for the z-scores is 0, meaning that ideally the middle point is right at the 0 level. And of course, if it's positive, then it's above the mean. If it's negative, it's below the 0 point, the mean of that specific data set. Now, if I do exactly the same for the reaction time data for picture naming, see here, similarly, the shape is almost the same, very similar. It's just the class intervals that changed here. That's why it's a little bit different. Then I can simply merge these two experiments and have my result for word reading and picture naming together and compare the male-female differences. Now we can compare males and females, and this is what we get out of SPSS if I group my subjects according to whether they were males or females, regardless of which experiment they took part in. I can see that overall females were faster since their mean standardized reaction time scores were lower than the average as compared to that of males, which was 0.5. So please notice this minus 0.3 something is slower in reaction time than that of males, which was average half standard deviation above the average reaction time in whatever experiment they took part in. So this is a very great way to deal with this kind of discrepancy if you have raw data that you want to compare. Let's have some practice. Calculating z-scores is really simple. You just have to use this formula. Calculate the standard scores for this data set. The mean is 120, standard deviation is 12. So 120 obviously will be whatever the formula is. Since we take 120 minus 120, the result will be 0. Then we have 108, resulting a minus 1, 144 plus 2, because it's 2 standard deviations above the average, etc., etc., etc. Please practice this. Okay, the other question, try to describe a research problem where the z-scores would be appropriate to use. You could come up with any kind of interesting topic that you desire. Let's turn to our next subtopic here, normal distributions, which the starting point is the z-scores that we've just discussed. This is summarized in chapter 6 and some pages in chapter 10, so please check them out both if you need any assistance with what I explain here. So let's create distributions, and I quickly give you a problem. Let's think of 10 numbers between 1 and 5 at random and write it down. It's really important to write it down since, just remembering it won't help. So write it down. Okay, I have my numbers. Now imagine that you've done the same and have written down 10,000 numbers. That's just important because remember, big enough data sets are a must. So, question, what do you think? And I already solved the result here. If we graphed all your data, what would be the shape of the histogram? Of course, it might deviate around the same frequency, but ideally your distribution would be just a flat line. So this would be the ideal distribution after like thousands of data. Why? Because if you're really thinking of numbers at random, then 1s, 2s, 3s, 4s, 5s should come up with the same frequency. Now, let's do something different. Let's create another type of distribution. And sorry, again, I sold the solution. But now, let's calculate the sample mean based on the first two random numbers from our previous task. Okay, so this is the task. Just take the first number, two numbers. For me, it's 1 and 4. And average it down. So that's 2.5. Etc., 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 etc. Do the same for the rest of your random number pairs. And again, imagine that you've done this for all 5,000 pairs. And the question remains, what will the shape of the histogram be like? Well, this is not really a cellar because it, doesn't really show you the result. It's kind of a random deviation here, but ideally you will have something revolving around 3. So 3 will be the most that you get, and the rest will follow to the both sides. Okay, so let me revert to the central limit theorem. Sampling distributions of means, any kind of mean, but if you're asking about the mean, kind of the central tendency, tends towards a normal shape as the sample size increases. But here sample size is a very important factor. And it's important that it's regardless of the shape of the population the distribution originated from. But the selection has to be random. That's a must. So this is a normal distribution. And let me show you it on a sample from the internet, YouTube, and maybe this will work. So here they are taking, you can see the count here, 700, 800, 900,000, etc., etc. And the little difference is even out, and by 5,000, the mean values, so these are means, go towards a beautiful bell shape that we call normal distribution. Okay. Interestingly, these are all normal distributions. So this is the what we call the standard normal distribution. Well, which is used to construct tables for the normal distribution, where we have the variance, the standard deviation of 1. Here, obviously, it's a more peaked distribution. This is a more flat distribution, but these are all normal distributions. Let's see the most important properties of a normal curve. So they are all symmetrical. In statistical terms, skewness is always 0. Also, this would be a negatively skewed distribution. This would be a positively skewed distribution, typical of reaction time studies, while people want to answer in the time frame they were given, and the right side is a little bit flat of the distribution. Also, they have this typical bell shape. So the cortices, again, another statistical term for the form of the curve, it's always 0. Now, the cortices represent extreme values. So if you don't have extreme values, then this value is 0. The mean the median, and the mode will also have the same value, which is obvious because of this bell shape. And it's also true for all of these distributions that although there's a trend towards the axis, the real empirical distribution never actually touches perfectly, tail never actually touches the horizontal axis. So in theory, this line goes on forever, forever, and forever. Of course, when we do empirical studies, this perfection is not true. Nonetheless, we can all say that 99.8% of the values vary within only 3 standard deviations around the average, and 95% of values vary in between 2 standard deviation plus and minus, and the same is true 68% for 1 standard deviation. We will use these numbers. These are very important numbers. They will be spelled out on the formula sheet, and we will make some calculations using these numbers. Probably the best example is the IQ scores, to go from IQ scores to standard scores, and let's see how it's done. Of course, this is a standard normal distribution where the mean is always 0, as we've stated, and the standard deviation is 1. So let's have some good practices here. First, let's use the z-score and standardize the weight and the height values of 3 students and compare these height and weight data directly by standardization. Remember, we can do that. So a student who is 82 kilograms and the mean value here is 78 kilograms, and the standard deviation is, the mean is 78 kilograms, standard deviation is 4. Then we can arrive, he is 1 standard deviation above the average. Then student 2 is 1 standard deviation below the average. And the third student is average. Same thing can be calculated for height, and thus we can make direct comparisons. For example, see some text here. Okay. Another example, if I state that IQ is 100, 15, meaning that 100 is the mean and 15 IQ scores is the standard deviation, and it's normally distributed. Then we can ask, what is the probability that a randomly selected person from this population, see, we can draw conclusions for the population just based on, well, notion here and calculations using statistics. So what is the probability that an IQ score of a person will be lower than 100? It's a very easy task, because where is 100? 100 is the mean itself. It stands right here in the middle where we have the 0 as a z-score. So how many people are below this point? Exactly half of the distribution. Thus, the solution is 50%. How about 70? That 70 is 1, 2 standard deviations below the average. 100 minus 15 and another 15 is exactly 70. So here we can state that this point IQ score 70 is right here, and we can read from the chart that it's 2.5% of the population here who is below this point. Similarly, you can state that many of the population, basically 99.9% of the population, is 3 standard deviations or 3 z-scores above, is below the score 145. So basically almost all of the people are here under this normal curve. These are the useful formulas for this part of the lecture, and this is an outline of just what we've looked at here, stating a very important fact that of course we were dealing in our examples with easy tasks, and that's what I will ask on the exam. But if you're interested in more detailed z-score values, you can find a table which explains how z-scores relate to frequency values and vice versa. And you can find very useful links on the internet to automated calculation methods that give you these points, and nonetheless you can use the statistical programs to calculate these for you. Thank you for your attention.